All right, first section, or first two sections we're going to do together. 5.1 and 5.2 is systems of equations. With any system of equations, no matter what size it is, if it's a 2-variable system, a 3-variable system, or an 86-variable system, it doesn't matter how big it is. There are only 3 possible outcomes. One outcome is the most common one and the one that we like the best. It's when there's one solution. If it's a 2-variable system, you'll get x equals a number and y equals a number. If it's a 3-variable system, you'll get x, y, and z, or whatever variables they're using in the problems, okay? One solution, that's what we want. One answer for each variable. That's what that means. Other possibilities are that you have answers, but you have so many of them, it's infinite. Infinitely many solutions. So you've got answers for x and y, but they are there's so many of them we can't just say, hey, this is the answer. There's more than one. Other words that go along with that you might see on the final exam, you won't see it from me, but on the final exam, sometimes when they ask, is there one solution, infinitely many solutions, or the other option? One solution, they'll call it consistent and independent. Consistent meaning it has answers. Independent means there's only one place that they meet up. If you're independent, my wife and I are pretty independent people, so we're the only place, we really go together is when we're together, and at home. So we go our own kind of direction outside of the house. So independent means you're going your own direction, but one spot you've got an answer. If it's infinitely many solutions, it's consistent and dependent is another word for that. Okay, consistent meaning you've got answers. Dependent meaning that you follow along. Whatever one line does, the other line does the same thing. That's dependent. So that's infinitely many solutions. Those are I guess what we'd say the mathy words for that is math speak for one solution is consistent and independent. Infinitely many solutions is consistent and dependent. Just most of the time you're going to hear me say one solution or infinitely many solutions, but you need to know these other words just in case you encounter them in a future class or some other time. The last option is an option that doesn't take a whole lot of work, but it's sometimes harder to recognize. It's when there's absolutely no solution, that there's no place that the lines cross or the planes cross. No solution. The mathy word for that would be inconsistent. A little easier to remember there. If there's no solution, it's an inconsistent system. Out of that. Okay. So if you're dealing with linear examples, and this is probably the easiest ones to draw, if there's one solution on a graph, you would have 2 lines, a blue one and a red one. Oops, red one. There we go. How many places are those lines crossing, the blue and the red crossing? 1. That's what it looks like when there's one solution. In a 3-variable system, which is 3-dimensional, the best example I can give you as far as what that looks like graphically is maybe the corner of the room. And that's a compound corner. Let's look at maybe this corner right up here by the exit sign. You've got 3 planes coming together up there. You've got the brick wall here, the sheetrock wall here, and then the ceiling being the 3rd plane. Where they come together is just that one little spot in the corner, that one point. That's what it graphically looks like if you did a 3D graph. 3D graphing is very, very difficult to draw, and it's hard to visualize even though we live in a three-dimensional world. It's not the easiest thing to draw and show. Two variable systems or linear systems are pretty easy to draw. So we'll kind of stick to those as far as drawing our examples of that. But the idea is if there's one solution, it's one ordered pair. If it's three-dimensional, it's an ordered triple like X, Y, Z in order there. If there are infinitely many solutions, you got two lines. You got a blue line and a red line. If they're infinitely many, they're right on top of one another. They're touching each other an infinite number of times. One solution, they're only touching each other in one spot, one time. Infinitely many, it's laying right on top of it. So you can't even count how many times they're touching. Okay, so this is an infinite many. And then the last scenario with two-dimensional is if they're inconsistent or have no solutions. You got a blue line and a red line. What do we know about those two lines? They don't touch, and that's called what? Parallel. Yeah. In a three-dimensional world, there's more than one way for things to have infinitely many solutions. There's a couple of different ways. There's if two planes lie right on top of one another, and then a third plane cut into those, it'd be like you have two pieces of paper coming together, and then a third piece of paper comes in and touches them here. There's an infinite number of solutions there, not just one. Okay. Another way would be if they're all three separate, like you've got three pieces of paper, they're all meeting up at the spine of the book. That's another infinitely many option there. The no solution with three-dimensional would be you've got three parallel planes. So you got a piece of paper here floating, and then another one underneath it floating that never touches, and then a third one under that floating and never touches. So that's a three-dimensional representation of no solution. Another representation would be if you had two planes that intersect, and then a third plane could be like the table, and there's not one place that all three of them touch, that you have two parallel planes and one that's not parallel, then there's not one place that all three of them touch, and that'd be a no solution scenario out of that. So three-dimensional, definitely a little harder to grasp, but mathematically, the way we're going to solve it, it's no different in how hard it is to solve. It's just the same because we're going to use some graphing calculator as a tool to help us solve those. All right, so let's talk about the first way that we could solve a system of equations. We want to solve by substitution. Again, I go over these methods, substitution and elimination, because that will be handy when we do the nonlinear systems, because we don't have the nicety of the matrix in the calculator if we do nonlinear like we do with linear. So a substitution problem, you might have a system of equations where you have one equation is 2x minus y equals positive 2, and a second equation that says y equals negative x minus 2. In a substitution situation, what they're doing is they're taking what one variable is equal to. Here we've got y is equal to negative x minus 2. So we can take that part and replace y in the other equation, because it says y is equal to that. And the way I always explain this with my high school kids is like, if I got somebody sitting on the bench that's just as good as you, and you're tired, I can replace you, right, with that person that's just as good, and it's an equal substitution, right? It shouldn't hurt the team at all, right? That's what we're doing here. If y is equal to this, then I can replace y with that, and it should make things work better. Okay, so with substitution, we would replace y with negative x minus 2, so that would give us 2x minus parentheses negative x minus 2 is equal to 2. So it gives us an equation that has how many variables in it now? Or what variable in it now? There's a better way to ask that. It's only got x in it, right? So that's easier to solve than one that has x and y in it. Because all we've got to do is get x by itself, and we're done with that part of this equation. So if I do that, I'm going to have 2x. I'm going to distribute this negative 1 that's there. So that's going to be positive x and positive 2. And then simplify. X plus x would be 3x plus 2 is equal to 2. And then get x by itself. So I would then subtract x or subtract 2 to get 3x by itself. And that's 0 over there. And that's pretty easy division. Divide by 3. 0 divided by 3 is 0. So there I have an x value that I found. In order to find the y value with that, I'm going to take that answer and I'm going to plug it in for x right there in one of the other equations. I'm going to use this one that I've got circled because it's already got y by itself. You could plug it into the first one for x and then have to solve it for y, and it works. You get the same answer, but that's more work than we really have to do. So I'm just going to work inside here. Negative 1 times 0 minus 2. That'd just be 0 minus 2, which is negative 2. So there's our x and our y. Officially, the answers are ordered pairs, 0, negative 2. Or ordered pairs are x first, x comma y. That's the boxed in, the ordered pair is our official answer as far as for the whole system. So that's using substitution to solve it. That's probably not the way you're going to do any of them when you go to the quiz or tests in a couple of weeks. You're probably not going to do any of them by substitution if they're linear. If they're non-linear, then you'll have to do a little substitution, which is why I'm showing it, because it's a little easier then. All right, let's look at elimination. We'll solve by elimination. Elimination, I like this method better for some problems because it eliminates one of the variables and gives you a one-step equation to solve, which is really always nice when you got one step to do. 3x minus 4y equals 1. And then negative 3x plus 6y equals 7. Right. So here we have a system of equations. Notice that one of the equations isn't like example A where we had y equals. They're both in what we would call standard form for a linear equation. The x and y are on the same side. That's what usually triggers me to think elimination to solve, is when both variables are on the same side, whether it's linear or nonlinear. If both variables on the same side, I usually think elimination a lot of times is the best way to go. Here, what do you notice about the x's in this system? Got a positive 3x in the first one and a negative 3x in the bottom one, right? So they're opposites of one another. The great thing is that if you just add that system together, add the equations together, negative 3x and positive 3x are going to cancel each other out. Negative 4y plus a positive 6y gives us how many y's? Positive 2y. And then over here, we just got to add 1 and 7. 1 plus 7 is 8, right? 2y is equal to 8. That's a one-step equation that I know I can get the answer to, right? So that's why I like elimination, is because I always just get this one-step equation that just takes division to solve. So y is equal to 4. So even though that's easier, the getting the x value is a little bit more difficult on this. You're going to have to take 4 and plug it into one of those equations. It doesn't matter which one. I usually just pick the top one and plug in 4 for y and solve that problem. That's going to be 3x minus 8, or excuse me, minus 16 is equal to 1. And then I would add 16 to both sides to get x by itself. So 3x is equal to 17. And then divide by 3. So we get a fraction answer out of that. Just not a bad thing. So our ordered pair would be 17 over 3, 4. X always comes first. Again, showing you these, we'll need this skill next week when we do nonlinear. But the idea here is that there are ways to solve it without a calculator. I'm about to show you how to do it with the calculator to help you out there with that. Okay. The way you want to solve that with the calculator, and this is the method that I think you'll employ most of the time, is using an augmented matrix. You know, the TI-84 family. Okay. So we're going to take a system, 3x minus 4y equals 1, and then 2x plus 3y equals 12. That's our system of equations. What we want to do is write in our calculator an augmented matrix. And that augmented matrix is going to take the coefficients of x and y and put them on the left. And then you're going to have 3 columns. You're going to have an x column, a y column, and the solutions column. Okay, so we got 3, -4, 1, 2, 3, 12. That matrix, when you name the size of it, it's called a 2 by 3 matrix. 2 rows, 3 columns. 2 rows, 3 columns. 2 rows by 3 columns. All right. Now, we want to put that into our calculator. All right. So, TI-84, whatever version you got there. If you've got the 83, it's going to work exactly the same way. This is one of the things that's not any different. Okay. So, to get to the matrix menu, you've got to hit second. And then there's a X inverse button. It's the 4th one down. It's the one it's highlighted in red here. And you should get to a menu that looks like this. Then I'm going to press over to edit. Because I need to enter in my matrix. So I got to edit a matrix. So I usually just pick A, the first one there, and just hit enter. And then the first thing it asks you is for the size of that matrix. Ours is a 2 by 3. 2 rows by 3 columns. 2, enter, 3, enter. I can get 3 there. 3, enter. There we go. And notice how mine changes the way it looks. The 83, I think, does. It just has, it doesn't look exact, the bracket doesn't look exactly the same. I think it breaks it up a little bit, but it does the same thing. It's not different. Now we're just going to enter in that matrix just like we've written it down. We got 3, -4, 1. Is that right? So the coefficients, 3, enter, -4, enter, 1, enter. And the second row is 2, 3, 12. Okay. Enter that matrix into your calculator. Everybody got that in? I don't want to leave anybody behind. Then hit second, quit. Gets us back to the regular calculator screen. Now we got to go back to the matrix menu and tell it to do something. So how do I get back to matrix? Second, inverse, the button below the math button. All right. Now, look at the names list. I've got a 2x3 there listed in A. So that tells me it stored that one that I put in. What I want to do is go to the math menu. So I'm going to press over to math. And then I'm looking for a command that's called RREF. And I think your best bet is to press the up arrow to get down to the bottom of the list, because it's down at the bottom, toward the bottom. RREF. Mine is on choice B. I don't know if yours is the same call letter, but choice B. RREF. That's the one we want. Okay, so I'm gonna hit enter. Then I need to tell it what to do RREF on. So I need to go back to the matrix. This is where I pick up matrix A from the names list. You don't have to close the parentheses here, but I do, just because my brain says you have to, but you don't have to with the calculator. It understands, hey, that's the only one they're doing that to. All right, now, all you got to do is hit enter after you've done that. What this does is it creates, through RREF, you get this matrix back, 1, 0, 3, 0, 1, 2. What that tells us, this row tells us that X is equal to 3. The second row tells us that Y is equal to 2. Remember the columns, there's an X column and a Y column. Well, here we got a 1X in this column, no Y's, and it's equal to 3. That's what that row is telling you. This is no X's, 1 Y is equal to 2. That's what that's telling you. Okay? The RREF, what it's going to do is it's going to get this to ones and zeros. That third column is going to be your answers for X, Y, and if we get to the 3 variables, it's going to be X, Y, and Z. Know that. So X is 3, Y is 2. Ordered pair, 3, 2. Your equations, though, have to be in standard form, like X, Y equal to a number, for you to do it this way. You may have to do some work to move them around. Let's do an example where you would. We got 3x minus 2y equals 4, and then 4y equals negative 5x plus 8. So this one, if we're going to use the matrix utility to solve this, we need to get both equations in the right form. The second one is obviously not in that form, so we need to get x back on the side that 4y is on. So how do I move this 5x? I'm going to add it. So that's going to give us 3x minus 2y equals 4, and 5x plus 4y equals 8. So I just move that around so that our system is in the right order. You got x's in a column, y's in a column, plain numbers in a column. That allows us to type into our calculator this matrix. Three, negative 2, 4, 5, 4, 8. Again, I would go second matrix, go to edit. I'm going to use matrix A again because it's already the correct size. And then you just type over the top of whatever's already in there. So 3, negative 2, 4. Then you got 5, 4, 8. And just check, make sure you got that matrix in there correctly. And then I need to do RREF on that again. So matrix, math, RREF. What that stands for is reduced row echelon form. Is what that stands for. Not that you really have to know that, but I might ask you, well, what's RREF? I get a decimal back. We usually don't like decimal answers. How do I get the calculator to give me the answer in a fraction form? Math enter. That's the beauty of the matrix style of solving. You hit math enter, you can turn that decimal solution back into a fraction solution, which is wonderful. So 16 over 11 is x, and y is 2 over 11. So there's our x and our y, and then we get the ordered pair, 16 over 11, 2 over 11. Again, that ordered pair is your official answer, but sometimes they may just ask you for x. The RREF, again, is called reduced row echelon form, but you might also hear somebody say Gauss-Jordan method. There was a guy named Gauss was his last name, and then another fella whose last name was Jordan. I don't think it was Michael, but Gauss came up with putting it in a matrix and solving part of it, and the Jordan guy came along and took what Gauss did and said, I'm going to do a little bit more with this, and I'm going to get it down to that 1 or ones and zeros there. Gauss got the 1 in the first place, and then he did substitution to finish it off. Jordan came in and said, if you do a little bit more with your matrix, you'll end up with both answers written in your matrix. So Gauss-Jordan is what they call that. Gauss-Jordan elimination or solving. Gauss-Jordan method of solving, but it's reduced row echelon form is what they called that when they got done. All right, so we've done 4 examples. All of them had one solution. So what's it look like when there's infinitely many solutions or no solutions with this? So let's look at something that obviously has one of those, since he said that. Here's our system. 8x minus 2y is equal to -4, and then -4x plus y is equal to 2. Is that in the right order and set up to put in a matrix? Yeah, so we know we're going to have this matrix 8, -2, -4, -4. What's in front of y there? 1 and 2. So we're going to put that matrix in for a calculator and run RREF with it. And I want you to see what the matrix looks like at the end. Freeze that. Again, we're getting second, inverse, edit. Still working with the 2x3, so I'm just going to use this one. So 8, -2, -4, -4, 1, 2. And then RREF on that matrix. And one of the shortcuts with the newer calculators is you can just press the up arrow until you get that highlighted, RREF-A. If you hit enter, it'll recall that command. But I put a different matrix in the part A, so it's going to use the new one that I put in. That saves you maybe a couple of keystrokes. Even if I hit math, enter. What do we notice about this matrix? We got 1, -1/4, -1/2, and then that bottom row is all zeros. If the bottom row tells the tale. if the bottom line is all zeros, no matter what size the matrix is that we solve, if the bottom row is completely zeros all the way across, that right there tells us that there's infinitely many solutions. If the bottom row is all zeros, it's infinitely many solutions. Doesn't really matter what's going on above that. It's the bottom row. That's the one we look at. On the previous ones, we got that bottom row. We had a 1 in that spot there. There wasn't all zeros there. There was some zeros, but there wasn't all zeros. So if there's all zeros in the bottom row, again, it's infinitely many solutions. Let's put this one in a matrix. 3x minus 2y equals 4. And then negative 6x plus 4y is equal to 7. Second matrix. Edit 3. 3, negative 2, positive 4, negative 6, positive 4, 7. Again, I'm going to go RREF of matrix A. There's some decimals in there. I'm going to hit math, enter, just so I don't have to write out those decimals. So I get 1, negative 2/3. There's a 0 there, not that that matters. 0, 0, 1. That bottom row tells the tale. What is this bottom row saying? It's saying 0 x's plus 0 y's is equal to 1. If I take no x's and no y's and I add them together, can I get 1? 0 plus 0 is never going to be equal to 1, right? So that creates a false statement, which means that there's no solution to this system. Okay, anytime that bottom row has all zeros and it's equal to something else on the end, it doesn't have to be a 1, it could be anything else, but it's anything else in that spot right there, it's no solution. Or it's an inconsistent system. So the bottom row is going to tell us if there's one solution, no solutions, or infinitely many solutions, just by looking at it. All zeros all the way across, infinitely many solutions, consistent, dependent. Zeros and a number on the end. The very last one is a number, but everybody else is a 0. That's a no solution situation, or also known as an inconsistent system. All right. So we've done 2 variable systems. Let's look at a 3 variable system and see how much the same it is. It's not any different. Okay. If we're looking at a 3 variable system, we got x minus y plus 5z equals negative 6. And the second equation is 3x plus 3y minus z equals 10. X plus 3y plus 2z equals 5. So a little bigger. But if we're going to use a matrix to solve it, what size is that matrix? How many rows will it have? Yeah, 3 rows, 4 columns. 3 rows because how many equations do we have? 3 of them. 4 columns because we have an X column, a Y column, a Z column, and then the solution, what they're equal to column. Okay, so that's a 3 by 4 matrix. Out of that. That 3 by 4 will be 1, -1, 5, -6, 3, 3, -1, 10, 1, 3, 2, 5. We're going to put that into the calculator. Second matrix. Edit. We'll make matrix A 3 by 4 this time. 1, -1, 5, -6, 3, 3, -1, 10, 10, 1, 3, 2, 5. Be very careful before you get out of typing in that matrix. Go back and check to make sure you got all your signs right and the numbers in the right place. Putting a wrong digit in the place of a matrix is kind of like dialing the wrong phone number. You get something completely different. You know, if you call 1 digit off of the phone number, it's not the same people. So if you get 1 digit different inside of that matrix, it's not going to get the same answer. You're not even anywhere close, and it would be impossible to work backwards and find it. Other than looking at your matrix and saying, "Hey, you just missed. You put a +1 in instead of a -1." So you got to be careful of that. Okay. So second, crit, and then we go to matrix, math, RREF, and then we want to pick up the matrix that we put in. Does this one have a solution? Look at the bottom row. Is it all zeros all the way across? No, so it's not infinitely many solutions. Is it all zeros and then something else? No, we got a 1 right there. So that tells us, hey, you got an answer. You got X, Y, and Z there. So through the magic of RREF, we now have 1, 0, 0, 1. Wow, put so much space there. And then 0, 1, 0, 2, 0, 0, 1, -1. That's the matrix, solution matrix to this. And so our answers are X equals 1, Y equals 2, Z equals -1, or the ordered triple, 1, 2, -1. All right, so we're taking just a 3-variable system and applying the reduced row echelon form method with the calculator. Same rules apply about the bottom row. If all of it is zeros, then it's infinitely many solutions. If it's 3 zeros and a number, then it's no solution. Here we have 2 zeros and 1 and a number. That means we have an answer. So be careful with that. But a 3-variable system, as far as how we're going to solve it, it's not any more difficult using the reduced row echelon form tool for our calculator. So definitely have fresh batteries on your calculator when you look at this stuff. Okay. All right. That's section 5.1 and 5.2. Yay. Let's get section 5.3. Not a whole lot left here, guys. So determinants. DETERM. Determinants of a matrix. Determinant of a matrix is one of those things that defines whether it can be inverted or not, which is important if you're going to use determinants to solve a system of equations, which we're not. Our main goal with determinants in Math 110 is just to calculate them. So determinants, it's kind of like a property is the way we treat it in Math 110. It's a property of a matrix, what its determinant is. Okay? That just defines what it can do. Yeah, it's kind of like the name. It's a hammer. It means it can bang on things. It's a screwdriver. It means it works with screw. It's a drill. Puts holes in things. That sort of thing. So a determinant is like a property based on that, and based on what the value of it is. But determinants only happen with square matrices. Matrices is the plural for a matrix. A square matrix is something like that is 2 rows by 2 columns, 3 rows by 3 columns, n rows by n columns. So that sort of idea. It's got to have the same number of rows, same number of columns to be square, and then we can calculate the determinant based on that. I'm going to show you how to calculate a 2 by 2 determinant by hand. But anything bigger than that, I'm not going to worry about you calculating it by hand. It can be done. It's not. It's pretty tedious to do that. 2 by 2 is short enough. Yeah, you can remember how to do it. And it's actually probably a little quicker than putting it in the calculator. But most of you will probably put it in the calculator and do that. And I'm going to show you how to do that too. But a 2 by 2, I usually just do by hand. A 2 by 2 matrix. To evaluate the determinant, and one of the ways it says determinant is using DET for the abbreviation, and then they'll put the matrix there beside it, A, B, C, D. We'll use letters here to start off with. In order to find that determinant, you multiply diagonals. A times D minus B times C. And that would get you the determinant of a 2 by 2 matrix. You multiply left to top left to bottom right, subtract away top right times bottom left for a 2 by 2. And I'm going to show you that with a calculator too. So, sample A. Let's find the determinant of 2, -3, 5, 7. You might also see this written in this form without the letters DET in front. And instead of square brackets, they put just straight up and down lines. Looks like absolute value lines, but that also means find the determinant. Different notation meaning the same thing. It's kind of like y and f of x are the exact same things. So not always. Okay. Now, 2 times 7 minus -3 times 5. That's 14 minus -15 is 29. The determinant is 29. Whew. What does that mean? It means it's invertible, but because it's not 0, but that doesn't really help us any in Math 110. If you take a linear algebra class, if you go to school, if you're and you probably wouldn't have to take that unless you're going into engineering of some sort. Linear algebra, electronics uses a lot of linear algebra stuff. So if you're going into that sort of engineering, you're gonna get a lot more of this kind of stuff going on. And they're going to give you some other handy things that could be nice with that. I'm going to show you how to do that with the calculator, though. So with the calculator, you're going to go to the matrix menu, and you're going to put in that 2 by 2 matrix, just like we've been putting in these others. It's going to be a 2 by 2 this time. So we got 2, -3, 5, 7. And then you're going to go to the regular calculator, put second quit to get back to the regular calculator screen. We want to find the determinant. So we're going to go back to the matrix menu, and we're going to go over to math. The good thing is with this one, you don't have to go anywhere. DET is right there at the top. Okay, so we're just going to pick that choice, DET, and then we're going to tell it what to find the determinant of. We want the determinant of Yeah, I bumped my cord. Velcro is stuck to the floor. Determinant of matrix A is the one I put it in. So wherever you put that matrix, go get it. Second matrix, I put it in matrix A. 29. So it cranks it out for you. You can do it with calculator. You can do it by hand. I'm not going to test you on your capabilities of finding a determinant by hand. You're welcome to use the calculator the whole time if you want to. I just usually don't on 2x2s because it's just two multiplications and a subtraction. I can usually do that faster than I can type them in because it's short. Anything bigger than that is many more calculations than that. Like a 3x3 is 1, 2, 3, 4, 5, 6, 7, 8, about a dozen calculations that you have to make to get the determinant of a 3x3. If you went to a 4x4, it grows exponentially from there. So it's a lot more calculations that you have to do. So that's why I say anything bigger than 2x2, I'm not even worried about you doing by hand because that's too many calculations for you to, it's just arithmetic, and I'm not really into testing you on arithmetic. The standard says teach you how to find a determinant. I'm teaching you a way. So let's look at a 3x3. Do what now? It determines whether or not you can invert that matrix, which means it also can determine if a system of equations has solutions or not. It's a yes or no. If the determinant is something other than 0, then yes, you can invert it, and yes, if these were like 2, -3, 5, and 7 were the coefficients of x and y in a two variable system, this being 29 would tell us that the solution that particular system has solutions. That's the application of them. There's some other applications of them that are above my head, so I don't know that I've never had. All I had was a linear algebra class. I don't know what the engineering applications are, but I know my roommate who was an engineering major made reference to, well, it's just a matrix and you just find the determinant. He said that all the time. I was like, whatever. I took one class on that. It was one of my favorites, but I didn't really pursue it any. All right, so let's get the determinant of a 3x3. 6, 2, 4, 8, 9, 3. 4 looks like a 24, so let's put it out here. 1, 2, 0. Again, I'm using the absolute value style lines here to indicate determinant. They could also write it, with a bracket and write the letters DET outside of it. Understand that is exactly the same thing. Okay. So we're going to put a 3x3 matrix into our calculator and find the determinant of it. Second matrix, edit, trace, trace, and 6, 2, 4, 8, 9, 3. And the determinant of matrix A, -2. Is that what you guys got? Hope so. If you did, then you put it in right. If you didn't, you probably typed in something wrong. Again, one digit off gets you a completely different person on the phone book. So one digit off in a matrix gets you a completely different determinant out of that. So, but very, very simple idea. Be able to find a determinant. I've checked box on that standard. All right, let's do some operations with matrices in the next section. We're going to skip over to section 5.7, properties and operations with matrices. easy stuff here. All right. So let's do row operations first, because they always put this on the final. And row operations, what happens when you're calculating, when you're doing those systems of equations, and doing that RREF with the reduced row echelon form, what it's doing is it's doing a ton of row operations where it's taking like row 1 and adding it to row 2 and getting a result and replacing row 1 with it. And then it does another one. But it does the right ones in order to get a 1 in the first position, a 0 after that, and then 1s and 0s in the right spots. Your calculator has an algorithm. It's pushing it through. I don't know if you've ever seen, there's an ultimate algorithm for solving a Rubik's Cube that if you do this, you will stumble into the solved form of the Rubik's Cube at some point. Your calculator has an algorithm that does that for systems of equations. The larger they get, the more times through the algorithm they'll have to go. But it does that work. Those row operations are what it's doing. So one of the standards here is for you to perform a set of row operations given a matrix out of that. So I'm going to show you how to do that. Row operations is a really easy thing. You just got to be careful about what you're changing. If you know which one you're changing, that's the only one that's changing. Okay, so here's our first matrix that we want to do a row operation with. 2, 4, 7, -5, 8, 3. Okay. We want to do row operations on that particular system of equations, or matrix came from a system of equations, or we can assume it did. Okay. The row operation that we want to do is R1 is equal to 2R2 plus R1. Okay. Let's decode the message. What this is saying is R1 is equal to this change. So we're changing row 1. That's what this tells us. Whatever it's equal to, that's the one that's changing. The other row in the answer is exactly the same. So if we're changing row 1, that means our answer better have exactly the same thing in row 2 as is what's right here. Okay? So this says take 2 times row 2 and then add it to what's in row 1. So we're going to take 2 times -5. We're going to add it to 2. So that'd be -10 plus 2 should be -8. In our answer, the new number that's right here is going to be -8. Okay? And then we'll do the same thing for this 8 and the 4. 2 times row 2, 2 times 8, 16, plus 4, 20, right? So there's a 20 that's going to be right there. 2 times row 2, 2 times 3 is 6, plus 7 is 13. So we're going to change row 1 on our answer. So after we've applied this row operation, the second row is -5, 8, 3. The first row, let's go back through it again. He said 2 times -5 is -10, plus 2 is -8. So that's what goes in that position. And then we say 2 times 8, 16, plus 4, 20. That's what goes in that position. 2 times 3, 6, plus 7, 13. We've performed that row operation. Okay. Not rocket science. Okay. Just taking the instructions they give you. They tell you exactly what to do, and they tell you to change which row. They're going to tell you which row to change. Let's get another matrix. Something a little larger. 6, 23, -21, 7. 3, 21, -27, 12. One more row. -8, 10, 2, -13. Need one more bracket big enough. here's the row operation we want to change. Row 3 equals 1/3 of row 2 plus row 3. 1/3 of row 2 added to row 3. Which row is changing? Row 3. So what's that mean about row 1 and 2? They're going to be the exact same thing that's already written there. So I'm going to hit 6, 23, negative 21, 7, 3, 21, negative 27, 12. I'm just copying those guys down because they're not changing. The only row that's changing is that one right there. It's row 3. All right. Now we got to do the math that it tells us to do. It says take 1/3 of row 2 and add it with row 3. So 1/3 of 3. How much? 1. 1 plus negative 8. Negative 7. Good. Take 1/3 of 21. It's 7, right? 7 plus 10. 10. Take 1/3 of negative 27. Be negative 9 plus 2. Negative 7. 1/3 of 12. 4 plus negative 13. Negative 9. Okay, easy stuff. This is not something that I prescribe doing on the calculator. Okay, it's much more complicated to get your calculator to do this than it is to just do it. You can get the calculator to do it, but I can honestly say I've never done it with the calculator this way, no matter what, because it's just too tedious typing it in and going and getting certain rows, and it's just a mess to do. So I always just do that do it by hand, or separate operation out of that. Okay. So row operations, be able to do those. They always put one of those on the final exam. They give you a matrix and say, do this row operation. Which one of these is the answer? An easy problem, a give me. That's what I always say. Is that's a give me problem on the final exam. But they always put one of those on there, or have every year I've taught 110. They put one of those on there. Okay. All right. Keep bumping the cord. There we go. All right. So let's look at the next thing. Let's add or subtract matrices. So this is not rows. This is entire matrices. Okay. The rule for this is they have to match sizes. If they're not exactly the same size, you can't add them. You can't subtract them. They've got to be exactly the same size. Okay. The reason that they've got to be the same size, what letter we on C, is because if you take let's take a 2x3 matrix, 2, negative 4, 8, negative 10, 5, 11. If I'm going to add something to that, it needs to be the exact same size. So it needs to be a 2x3 matrix as well. I'm going to have something like negative 5, 12, 3, 6, negative 7, 2. And when you add matrices, excuse me, they got to be the same size so that you can add corresponding parts. Okay, whatever's in the first position, top row, first spot, adds the top row, first spot. top row, second spot, adds to top row, second spot. And that follows the whole way through. Right? They've got to be the same size in order to add or subtract. If it's a minus sign between them, you just subtract. That's the only difference. So they've got to be the same size. So this is a really, really easy thing. I usually don't do these in the calculator just because I can do that addition subtraction pretty fast. I'll show you how to do it with the calculator. It does it really, really nicely and easily. But you should get a 2x3 matrix back. So here 2 plus -5 is -3. -4 plus 12 is 8. 8 plus 3 is 11. -10 plus 6 is -4. 5 plus -7 is -2. 11 plus 2 is 13. We get that matrix back as a solution. If it's addition, you're adding the corresponding parts. If it's subtraction, you're subtracting the corresponding parts. If they are not the same size, it's an undefined operation. If you tried to do it with your calculator and it didn't, it would give you an error saying dimension mismatch because the dimensions of the two matrices don't match. Addition and subtraction have to be the same. So if I'm going to do this with the calculator, I would go second matrix, edit. I've got to put two matrices in here. I got 2x3. I just made this one up. So 2, -4, 8, -10, 5, 11. 2, -4, 8, -10, 5, 11. -10, 5, 11. So I put that first matrix in, second quit, go back to the matrix, edit. I'm going to go to matrix B this time. It's a 2x3. And I'm going to put in that matrix. -5, 12, 3. -5, 12, 3. And then 6, -17. 6, -7. There. Yeah. Okay. Now, second quit, get back to the regular calculator screen, and then we're just going to recall those matrix names. So hit second matrix, matrix A, plus second matrix, and then select matrix B. And it'll spit back out that matrix that we found by just adding the corresponding parts. If it gets pretty large, then it might be worth typing it in because you may be, y'all are probably faster at typing it in than I am. Of course, especially when we had to do it on here. Thing stinks for that. So, but the handheld, you can use your thumbs. Makes it easier. Okay. So addition, subtraction, really easy thing. I usually do it by hand. I don't usually use the calculator just because it takes me too long to type them in. All right. Now, next thing would be multiplying matrices. Multiplying matrices. It is not like addition or subtraction. It is not like regular multiplication either. Okay. Regular multiplication, if I said 2 times 3, I'd get 6, right? And if I changed the order and got 3 times 2, what do I get back? 6. Same thing. Matrices, when you multiply matrices, it's not commutative. So it does matter what order things are done in. So matrix A times matrix B is not the same answer as you would get if you did matrix B times matrix A. It may not even be a defined operation. Multiplying matrices, it's not commutative. And then columns of the left matrix must match the rows of the right What does that mean? Okay. It means the size of our matrices. If we had a 2 by 3 matrix and we're multiplying it times some other matrix, the columns are 3. There's 3 columns in that left matrix. Then the right matrix has to have 3 rows. Those numbers have to match. If they don't match, if what's here in the middle doesn't match, then it's not defined. Okay? So size of your left matrix, size of your right matrix. The numbers that are touching each other in the middle have got to match. If they don't, then it will not multiply. Okay? When you do that multiplication, like this one does match, the answer is these things on the outside. A 2 by 4 is what the solution gets. All right. Let's look at an example. Here's matrix A. 1, -3, 7, 2. Here's matrix B. 1, 0, -1, 2, 3, 1, 4, -1. D. Skip something. Must have. May have taken. No. This one letters aren't lining up with what I wrote. Yeah, that's it. I've done everything though. All right. So we're going to do A times B. So what size is matrix A? 2 by 2. What size is matrix B? 2 by 4. Those numbers in the middle, they match. That means we can go ahead and do this. That's going to equal a 2 by 4 matrix when we get done. The outside edge. 2 on the left, 4 on the right. That's what size our matrix will be when we get finished multiplying. Okay. I do not expect you to do this by hand at all because it is a lot of calculations. You have to take row times column, so we have to take 1 and -3 and multiply it times this row, add those results together. That gets you one spot. Then we take this row times this column. First row times the third column. First row times the fourth column. So just to get the top row, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you're going to do the same thing on the bottom row. So it's 24 calculations to multiply 2 matrices together. I do not expect you to do that without a calculator. Okay. So we're going to put these 2 matrices in our calculator and get it to crank out the result. Okay. Second matrix, edit. Matrix A is a 2 by 2. 1, -3, 7, 2. Second bit. Edit matrix B. It is a 2 by 4. 1, 0, -1, 2, 3, 1, 4, -1. All right, so similar to how I did A plus B to get the addition, I'm going to do A times B to do the multiplication. So second matrix A times second matrix B. And there it cranks out What size is that thing? It's a 2x4, just like it's supposed to be. -8, -3, -13, and -1. Right. Nope, +5, sorry. Okay. There we go. And then 13, 2, 1, 12. 13, 2, 1, 12. Is that what y'all got? All right. What's B times A? Mismatch. Oh, so if I try to multiply those together, it gives me this error, dimension mismatch. The reason it's a dimension mismatch and it's an error is I look at the size of matrix A. The left matrix is 2x4. The right matrix is 2x2. These in the middle don't match. If they don't match, then it's an undefined operation. So you would write undefined. And there's nothing left. No reason. I mean, no reason to go any further with that as far as what you would need to do.
We don't need to switch them to make it right.
No. You just make sure you put it in the order that the problem asks for, and it's possible that you get some that say, "Hey, it's dimension mismatch." That means that it's an undefined operation. Yeah, don't swap them just to make it work. Do it in the order that it asks for. Okay. No matter what sizes you got, you can do that with the calculator. Just put them in there and get it to multiply them for you. Just got to be careful putting them in. All right. All right, let's look at matrix equations, which are pretty easy, actually. Matrix equations are really close to addition and subtraction matrices. It's really what they are. If you've got two matrices that are equal to each other, so as you say you had 2, 1, W, N, different variables there. And then you've got another matrix. It's the exact same size. Because if it's going to be equal, it's got to be the same size at least. X, Y, -1, 0. From this problem, we've got a 2x2 matrix over here. We got a 2x2 matrix over here. If they're going to be equal matrices, what does that mean about each spot? They have to be the same. So 2 is actually equal to what? X. So the solving that happens here is you say, oh, well, X is equal to 2 because they're in the same spot. Okay? So they give us X is equal to 2. What's Y equal to? What's W? N. Not much work to do on this one, but the idea is, okay, matching spots go together. Where they get a little more fun is with one of these. That's the word. 7 is fun. 7, X, and 3, 5, 10, Y. Plus 8, -6, 10, 5, 16, 7 equals. What size are both of those? 2x3. So that means when these two add together, they got to be equal to what size? 2x3. 15, 10, 13, 0, 26, 14. Okay. Now, corresponding parts go together. So if we're going to add these two matrices, 7 plus 8, what's it equal to? 15, right? So that's the right spot. X plus what? -6 is equal to 10. Oh, we got an equation that we can solve it. If we need to find x, then we've got to just set up x plus -6 equals 10. Because here we have an x, here we have a -6, here we have a 10. That's where I'm getting that equation. Those corresponding parts that have the variables in them. Okay. We could solve that. Add 6. X is equal to 16, right? What's the equation to find y? So where's y? Bottom right. So y plus what? 7 is equal to 14. So we set that equation up. And that's pretty quick and easy to solve. Y is equal to 7. These are not systems of equations. They're matrix equations. So you, inside of the matrix, you're pulling equations out of them. Okay? It's not a system of equations. Even though they'll use x and y quite a bit, it's not a system of equations. You're just getting an x equation, solve it. Get a y equation, solve it. Okay. So it's not a system of equations. It's just a matrix equation. And it's just that. Find the corresponding parts. Set up your equation. It's really a simple idea. It looks monster hard, but it's really, really easy. The equations they give you are not going to be hard. You just got to pull out the right pieces. Questions about that? Last section of the night. And it's 7:15. No. No, this one's actually pretty easy. It's a calculator thing too. 5/8. Inverse matrix. Or an inverse matrices. So it's the multiple of it. So inverse matrices. An inverse of a matrix is similar to the inverse of a number. 3. What's the inverse of 3? That's right. That's the key there. 3 to the -1 power is 1/3. With a matrix, why is 1/3 the inverse of 3? Why are they inverses? You may have never been told this. Probably not. What happens if you multiply 3 times 1/3? You get how much? It's 1. So if you multiply something times its own inverse, you get back 1. All right? The multiplicative inverse multiplication, is always going to get you back a 1. In matrix land, I guess is the best way to say this, when you're dealing with matrices, if you multiply a matrix, think about how we solved equations way back in 100 when we were doing some easy equations. Maybe you had like 2/3 x is equal to 18, something like that. You could take, how would you get rid of the 2/3? You multiply by the what? The reciprocal, which is actually the what of 2/3? The multiplicative inverse is what its real name is. We called it the reciprocal which is a synonym for multiplicative inverse. With matrices, what happens over here on the left side with the 3/2 times the 2/3? What's that turn into? It cancels out and becomes 1x, right? So with a matrix, if you multiply a matrix times its own inverse, it's going to cancel it out. That's what happens. Inverse matrices, we're not going to use them to solve systems of equations in Math 110, but the idea of an inverse matrix could be used to solve a system. We're going to use RREF to solve systems because it's easier. An inverse matrix, though, we introduce that idea in case you decide to go a little further in math and take some sort of class where you're having to do that. If you decided, hey, I need another math credit, I'm going to take Math 140. Math 140 takes it a little further, even though this takes the place of 140, 110, and 100 does together. We don't go quite as deep as they do in 140. And spread it out over 2 semesters. So here, that canceling out is the idea. So if I have a matrix A, it's this: 1, 0, 3, 2, -2, -1, 3, 0, 0. And they want me to find the inverse of A. They might even write it this way: A to the -1 power. That's the inverse of A. Okay. What I want to do, what kind of matrix is that, by the way? 3 by 3, which is also called a what kind? We mentioned this earlier when we were talking about determinants can only be done of what kind of square. Yeah, this is 3 by 3. If you're going to find the inverse, it's got to be a square matrix to find the inverse of it. If it's not, then it can't be done. Okay, so inverse matrix of a square matrix. That's what we're doing here. The great thing is our calculator is really good at that sort of stuff. So if I just type in the calculator, my matrix A, so I'm going to put that, and they go to second matrix. I'm going to edit, put in a 3 by 3 into matrix A. 1, 0, 1, 2, -2, -1, 3, 0, 0. Excuse me. Did I write it down wrong? Oh, it's a 3. Let's put it, sorry. Okay. I put that 1, 0, 3, 2, -2, -1, 3, 0, 0. Okay. There's my matrix. I want to find the inverse of that matrix. I'm going to hit second, quit to get back to the regular calculator screen. I'm going to go get that matrix with the name. So second matrix, matrix A. I've got an inverse button on my calculator. Right there underneath math. I don't hit second. I don't hit anything else. I just hit inverse. And it's going to put the -1 up there. That's A inverse. I hit enter. Ooh, bunch of decimals. That's not pretty. Let's make it fractions. Not that that's prettier, but it's a lot better looking than those long decimals. So math, enter, enter. 0, 0, 1/3. So A inverse, 0, 0, 1/3. -1/6. -1/2, 7/18. Last row, 1/3, 0, negative 1. 1/3, 0, negative 1/9. We have found the inverse of that matrix. Now, here's the thing with the matrix. When you used a 3/2 times 2/3, the reciprocal, when you multiply those together, they ended up being 1. With a matrix, if you multiply A times A inverse, you get what's called the identity matrix. And this one's a 3x3 because matrix A is 3x3. So this is the identity matrix, or I3 is what they call this. Identity. All this is theory stuff that you really don't have to know, but I like to, maybe it helps things stick if you know a little bit more than what you have to. So if I hit matrix A times matrix A inverse, there I got the one, the identity matrix, the I3 matrix, which is a 3x3 matrix with all ones in that main diagonal out of that. Okay. What that would allow us to do is multiply both sides by the inverse matrix on a matrix equation and solve for some vector. If you get into calculus, you'll do some things with vectors, and matrices and vectors work well together. So that's where matrix algebra can be helpful in being able to do that. So we introduce a lot of these things that you might need if you go further in math, not necessarily that you have to have. All right, let's look at another one, and then we'll be done for the night. Let's find matrix B is 2, negative 5, 7, 8. Let's find B inverse, just to get that practice. 2, negative 5, 7, 8. So 2 by 2. I'll confuse people if I put it in A. I'll put it in matrix B. 2 by 2. If you can type it in there, you can find the inverse. Definitely don't want to write that as your answer. Math, enter. And it should be able to turn that back into a fraction for you. 8 over 51, negative 5 over 51, negative 7 over 51, and 2 over 51. There's the inverse. If you multiplied matrix B times the inverse, you get the identity matrix back. Coincidentally, inverse matrices, when you multiply them together, that's the only matrix multiplication that's commutative. If I said matrix B inverse times B, that's the same thing as B times B inverse. That's the only kind that you could write it in either direction and it works out of that. So that's the kind of the result of that. Okay, so being able to find that inverse, that's my goal for you out of this. Here's some problems out of the book that could be helpful in prepping for your Canvas quiz for this week. We got Canvas quiz this week, labs, and lecture next week that covers the last 2 sections of Math 110. And then you'll have a Canvas quiz that just covers those. And then the last class meeting on the 23rd, I believe is the right date. Yeah. 16th, we got labs and lecture. 23rd, we got a couple of quick labs and then last exam. And then the 30th, you're coming in 6:15 for your final in this room. All right, so here at the end, folks, it's gone. This semester is absolutely flown. And again, I don't expect you to do all of these, but just some practice to get you on the right track. But you're not going into the Canvas quiz just blind out of that. So, all right, that's all I got for you. Y'all have a wonderful evening, good week. Email me if you got questions, and we'll try to finish this thing off. Get out of this class alive. Hey, I can. Let me just. Yeah, I can give you a rough. I don't have all the labs type grades in there for the labs, but they're not going to have as much effect on it as the test will. But yeah, I can definitely do that.